You're going to see some stuff you've seen before, and you're going to see some new stuff, and now we're talking about how these chemical reactions affect cell function. So here we go. Go ahead and get that down, get your blanks filled in, and I'll come back and tell you what I mean.
Lesson 4.
Most of our fancy words have foreign origins. That word metabolism is a Greek word.
To speed up.
Metabolism. We just say metabolism. I taught this in high school, so this should not be foreign to y'all. Depends on when you get out of high school, doesn't it? If you're an old person like me,
you go to high school there.
You might not know this. Because I taught it, I know it. But you youngsters in here, y'all should know this stuff. So let me talk about this slide, and because I'm going to use it to make my next test. So I need to clarify some things. First off, when I taught this in high school, I said every single reaction that a cell does, every chemical reaction it does, is under a big umbrella called metabolism. I think the definition basically is metabolism is a sum total of all the chemical reactions a cell carries out. And there are a heap of them too, baby. So any kind of chemical reaction that's happening in a cell, respiration, phosphorylation, all that, don't worry about the big words. But any reaction is going to be some kind of metabolism. Now, the very bottom tells you there's two categories. There's catabolism and there's anabolism. Remember the ion, the cat and the and? With catabolism, do you think you're building or tearing down?
You're tearing down?
It's like catastrophe. Well, your house is toward a hurricane. That's the catastrophe. Well, in this case, this is not bad. You're going to tear down the food you eat so you can use it, right? So catabolism, all digestion is catabolism. And you better do it. Now, when you get cut and you heal and you build new cells, is that catabolism?
Mm-hmm. You tear down.
When you're building new cells?
It's anabolism.
That's anabolism. So when you are reducing compounds, when you are destroying compounds, splitting compounds, decomposing compounds, that's catabolism. When your hair is growing, you're growing taller. You're making enzymes, you're making proteins, you're synthesizing. That is anabolism. But all together, we call it metabolism. So, you might get a question where, of the following types of metabolism, which two are catabolism and which two are anabolism? And I might list digestion, I might list dehydration and synthesis, I might list hydrolysis. Well, first off, in that word, dehydration and synthesis, what do you hear? Synthesis. Synthesis.
Making something.
Well, it had better be your answer. If you're synthesizing, what are you doing?
You're making something.
You're making. And so sometimes the answer is a giveaway. I call those gifts. A lot of folks, you see dehydration, and you go, oh, I'm dehydrating. I'm tearing it down. You're removing water to build. And I see why people will select catabolism for dehydration, because they think in a negative. They think, well, if you dehydrate, you're dying. Well, you are too. But in the process called dehydration synthesis, I am removing water so that I can hook things together. That is making. That's anabolism. And good God, there are thousands of examples. You don't know maybe 3 of them. But anyway, if you break a bone, before you can heal it, you must dissolve the old pieces of it. They'll be in the way. So when you break a bone, catabolism comes in and dissolves the piece of the broken bone. And you recycle those things. And then when you start to heal, anabolism kicks in and you make a callus, not like on your fingers, but where that bone heals and becomes bigger, that's called a callus. And you'll never break it there again, I guarantee you. You might break it above and below there, but that callus, it's like super glue. You won't break it there ever again. But you might break it above the callus in some other location. This arm here, I have broken it twice. Once playing football and once on a motorcycle. So you can break one twice. Now this is what I already told you. We're going to go ahead and put it in writing and get your blanks filled in. This is just one example. Let me ask you a question now. I know it'll come back and bite you in the butt one day. What organic compound is your chief source of energy? Name the one compound that is your fuel.
Is it carbohydrates?
Huh?
Carbohydrates?
I want something smaller than that. This thing I want is a carbohydrate. I want to know which one is it. Glucose. Yeah. Yeah, it's a carbohydrate. But when I said I want a specific answer, I want you to say glucose. Glucose is broken down to give you energy. That would be catabolism. When you break it down, you're destroying that sucker. For a good reason, though. Now, when you hook together amino acids to make a long polymer, we call it a protein, well, you're building that. That would be anabolism. When you put those nucleotides together to make DNA, and you actually hook them together, and that's also anabolism. But before you can do respiration, you've got to do digestion. You've got to eat that food. You've got to digest that food down to glucose, and then send that to your blood, and your blood then sends that to your cells. And your cell, it goes to your mitochondria, where the mitochondria actually do the process of keeping you living. You're the sum of your mitochondria, basically. When you have no food and you die, it's because your mitochondria had nothing to work with. And the cell died, and when your cells die, then you die. When you get sick, and you feel nauseated, and you have the urge to throw up, but you don't want to throw up because it's a violent reaction, or your head's throbbing, all those are signs that your cells are in stress. We can give you drugs, aspirin, to replace the chemicals that's causing the stress in the first place. So drugs really are basically a substitute for the chemicals your body is not really making. It works, that's how we figured it out. And most of our drugs come from plants, by the way. Most of them come from plants. Morphine is from a plant. You know where it comes from, folks?
Poppy.
Poppy. Same place cocaine comes from. So that plant can be used for good and bad. Good and bad. Somebody had a hand up, I thought. What you have?
Isn't there glucose-free food, or is that gluten?
No, that's gluten.
Okay.
That's gluten-free.
Why?
I don't know why. I know my wife looks for it, though. She likes anything gluten-free, she's going to buy. She's going to buy. She likes gluten-free, and I just like the way, if it tastes good, I'll buy it. If it don't taste good, I won't buy it. Because a lot of times you got to buy a whole portion, take one bite, and you can throw the rest away. So my problem with the cake, I buy me a cake, ate 2 slices, solid, and it gets hard as a brick, and I throw my cake away. I paid $8 for it or something.
Give it to the boys.
I like it when they slice it in half. Even in 4 is better than that, because I'm just going to nibble on it and then throw it away. I never eat a whole cake. My wife don't either, so I know I'm wasteful, but I still want the coconut cake. The coconut first I can eat probably, because coconut, boy, it's full of all that glucose. There's always a pathway to follow as a reaction occurs, and some pathways are very, very, very sophisticated. I think I'm going to show you one in a minute. Just actually blow your mind, not to make it hurt. I think I did. I know I put it on PowerPoint. In other words, this chemical's changed to this chemical, that's changed to that chemical, that's changed to that chemical, that's changed to that chemical, and that's changed to what you want. It's never just from A to B. It goes A to B to C to D to E, and you finally get the one you want to have. If you're missing any step in there, what's going to be a problem? You can't get to the end. Blood clotting is an example. For your blood to clot, there are about 26 steps that must happen one after another. And one of them involves calcium, and another involves a substance called fibrinogen. Now, if your diet is lousy, and you don't have much calcium, you're going to be a bleeder. Or if you have a gene defect that came from your mama and you're a boy, you're going to be a hemophiliac bleeder. That means you don't have the gene to make a thing called fibrinogen.
Factor 8 deficiency.
Which is one thing you got to have to complete the clotting process. If you don't have it, you can't finish. And and all these things are pathways. Some pathways are fairly simple, and some of them I don't even want to think about how complex they are, because it took years and years of 30, 40 scientists each contributing to get the whole picture. Things you see on here, one person didn't figure that out. It took many people talking together, sharing ideas to put the whole thing together. Now, enzymes, oh man, you got to have them. Enzymes make the reactions go. You've got to have them. And that's why I said they're crucial to metabolism. Most of the reactions in your body would not take place if not for your enzymes making them go. You couldn't digest that food in time to keep you alive. Enzymes make it digest in a few hours, but that is going to take you weeks. You'll be dead by then. So enzymes make it go fast. And it all boils down to basically energy. Energy is what keeps you living. Even when you heal and you're making new cells, that requires energy. And when you're growing larger, you're 5 years old, growing to be 6, to be 7. That, I know you're making new cells, but that requires energy. You cannot get away from energy. You got to have it. And enzymes make energy be released from compounds that would not release that energy had it not been for the enzyme making it happen. And enzymes, they're proteins now. Enzymes are proteins. And that's why we spend a lot of time discussing proteins, because by George, you got to have them. They're not just nice to have, you got to have proteins. Now, enzymes play a role as catalysts. Enzymes are catalysts. Some enzymes stop things from happening. And some enzymes make things happen.
Where are we in the book?
I don't have a clue. I'm teaching from knowledge. I would look up enzymes, I would look up catalysts to see where I'm at. Because that's the subject of my PowerPoint, of this slide. But I'm not the kind of teacher who needs that book to teach. I just know this stuff. And things I'm saying the book would agree with. But I ain't using that book. I'm using 35 years of knowledge and science. Young teachers can't do it this way. I mean, I have probably forgotten, I'm not bragging, I've probably forgotten more stuff than y'all ever going to know. I'm just saying, things I used to know that I don't teach anymore, I forget it. But I can quickly relearn if I had to. Like Spanish. I used to know Spanish. But I can't talk to anybody. So now I know C and hable and that kind of stuff. But if I went to Spain, I'd probably pick it up pretty fast again because I've been learning one time and I got a working idea of it. A lot of folks don't have a clue. But one thing, I happen to enjoy science. To me, it's not a chore to learn. I really enjoy it. My wife goes, anytime I go to bed, I said, honey, I'm on a roll. And she don't understand why I can sit there for hours and hours and just soak this stuff. I really like it. I should have been born 200 years ago. Then they'd be 10 organelles. I'd discovered all this stuff. That's all been discovered, so I'm here too late. But I tell you one thing, I do realize how smart those guys were back then to discover this stuff I have a hard time learning right now. They discovered it. I said, they're smarter than me. And I know Einstein is smart compared to someone like Newton. He's a dummy.
He had all the stuff like
Isaac Newton was he lived before IQ test, but the science, the math called calculus, he invented it.
Therefore, Einstein couldn't have done anything without Newton.
Exactly right. But even Newton said, if I did anything, I stood on the shoulders of others, meaning not by myself. I had help. Newton sat in church one day, had an earthquake. While folks ran, he watched the chandelier swing back and forth. And he's going, that's pendulum motion. And he got the formula for how the swing stops. I'd have run for the hills. But they might fall on me. He goes, you see Einstein's hair?
Yeah.
Would you call it well kept?
Looks terrible.
He had no concern with his appearance. It was his intellect he was concerned about, his brain.
Wasn't he colorblind too? So it was where
I do not know if he was. I know one thing. When he left Germany, he couldn't speak a dab of English.
And he always wore
And within 4 years, he was talking to everybody around him. When he came over here, he knew about the bomb. Hitler wanted the bomb himself, because Einstein had been working on the bomb. When he came over here, Einstein wrote a letter to
Roosevelt?
no, maybe Wilson. It wasn't Roosevelt though. But no one could read German. And so he just said to his scientist, read this thing, what's this guy talking about? And the guy read it. He goes, Mr. President, there's something he didn't hear about. And so the man translated it. And that became the Manhattan Project. It happened in 3 places in our country. And that was the development of the atomic bomb. People died making the bomb. And we just made 3 of them. It's the biggest bluff in history. We told Japan, we're going to bomb you to oblivion. We had 3 of them suckers. And one of them we dropped ourselves, make sure it worked. It worked. It worked real good. As a matter of fact, Enrico Fermi, which the element fermium is named for, there's also Einstein. We named things for these guys. Fermi, when he saw it go off, he went, oh my God.
Where they dropping
See, out west.
Los Alamos?
No, it's in the U.S. continental.
Look over there.
Yeah,
It
New
was
Mexico.
the Midwest. I don't forgot the exact place.
New Mexico.
But
Yeah, it was New Mexico.
see, Einstein has said, let's invite Japan over here and watch this thing go off. We'll call it truce. And Fermi said, no, if you push that button and nothing happens, we'll be a laughing stock. So Einstein goes, I see your point. So we didn't invite Japan over here. If they saw the bombs go off, would they have stopped fighting?
Probably.
Don't know. They had never, ever, Japan had never, ever, they were like 1,000-0. They had never lost a war, ever,
And they don't surrender.
ever. And here we were, a little country like us, and we had all the airplanes stuff, and we dropped that bomb. We flew across an airplane and dropped out leaflets saying, y'all leave. We got a bomb coming, y'all leave. So we warned them, but they didn't believe one bomb could do that. And we talk about killing civilians in combat. It happens all the time, folks. It happens all the time. As a matter of fact, it's the civilians who put pressure on the politicians to stop the war. Because the army generals, they ain't stopping nothing. They're going to fight to the death. As a matter of fact, they meant to fight. When we attacked Okinawa, which was part of Japan then, them folks leapt off of cliffs. They've been told that we were barbarians, we were going to rape women, cut off the men's head, and they fought to the death. They wouldn't give up and surrender because they've been propagandized how bad the Americans were. And that's why, to this very day, we're highly stressed. Do not shoot prisoners. Give them medication, give them food, make their friends want to surrender too.
Yeah,
Why do you think we didn't surrender to the Japanese?
because they treat.
They're going to kill us.
Yeah.
I'd rather die fighting than die with a hand tied behind my head, right? And that's how it happens. So, Japan had a lot of war crimes, but you see, Japan fought figured. I know because my father's brother, was killed in World War II, shot down by Japanese with hands tied behind his back. My father joined the Navy to kill Japanese and the war ended. He never in his mind got his vindication. And to this day, my father hates Japan. You can't even talk to him. I can see that. I never knew my Uncle Reeford. He was captured Guadalcanal. It was on his ship being taken to Japan, and our submarine surfaced. And he said, we're going to search that ship. And instead, the Japanese lined up about 100 men and machine gunned them off the side. Well, then we sunk the ship. And my uncle was among those machine guns. And my father, his brother, just, oh man. That restaurant called Tokyo's, I used to love to go to Tokyo's. My father would not even set foot in there. Because it was just that it was Japanese. And those people, they were nice as could be. But my father, was he prejudiced?
Just a little bit.
But would you call that?
He has
To be prejudiced,
he has actually.
does that mean you don't know, you just think that, don't know why? I'm wondering,
Well, he has good reason to be prejudiced.
well, I'm saying he had a reason, and I don't think,
Prejudiced.
according to the Bible, you're supposed to do what to your enemies.
Forgive.
Exactly. And my mama and my father, my mama said, her name is Paul. You want to go to glory, you got to forgive. And my father said, I just can't do it. My daddy is right now, he's 86 years old, and I worry about his soul, frankly. I ain't lying to you, because he don't just dislike him, he hates them. And if my brother been killed like that, now I think if he'd been killed in combat, shooting back and forth, my father been all right. But he was gunned down. Because in Japanese mind, if you surrender, you're less than a dog. You deserve it. In our mind, you're human, whether you surrender or not.
I take Taekwondo, and they make you learn certain things about Korean history, and it's all, we hate Japan, we hate Japan.
Korean and Chinese.
Yeah, the Chinese.
I mean, they
Koreans and Chinese hate Japan worse than my daddy did.
And the Japanese hate Japan.
And I know they all resemble each other to us, but in those two cultures, there's no love. There's no love lost. There's a lot of love lost in that case. But you're right. Well, the Filipinos hate Japan too.
Everybody over there hates Japan because
It
Japan
seems like-
slaughters them.
Well, Japan was. They almost ruled the world. I mean, look how big Japan is.
It's crazy.
And how much they took. Oh, where did soldiers come from? Somehow they got. Well, one thing that made you work for them.
Just like
When they captured you, you worked for them then. The Bataan Death March. They did for one reason, to kill Americans. They marched them to death. When you fell by the roadside, they'd bayonet you. You could carry your buddy, and you both fell. They've been at both of you. And you need to read some history about World War II. It's terrible. All right, but anyway, now Hitler was the one who worked with gas. He believed in using gas on the battlefield. I know in the Army we had gas, but I can remember the wind blowing. If it's blowing toward the enemy, fine. But the wind can change and blow back to me. So we didn't use, at least I know, I was taught first aid for gas. But I don't know, anytime artillery did it, they fired cannon. And I don't think we ever used gas. I don't think we did. I know we didn't use it then now. These are some videos that I found on how enzymes work. Now, I want to just grab one of them and go to the internet and let y'all see this thing. A lot of times, pictures work more than me talking to you. So let me just take and stop this show and highlight one of these and grab it. And then go to the internet.
Yeah.
And then come right here and drop that in the resource, and then go find it. I hope that thing's going to talk to you.
Enzymes. Enzymes are energized protein molecules responsible for all the biological activities going on in our 100 trillion cells, and are essential for every chemical reaction that takes place in our bodies. From digesting the food that we eat and unlocking the nutrients in it, to activating our immune system and producing energy in the body. According to Professor Paul D. Boyer, 1997 Nobel Prize winner, enzyme is a splendid molecular machine that produces ATP energy. Enzymes regulate the normal processes of digestion, absorption, waste removal, and are essential to every function that makes human life possible. Enzymes are not only the foundation of human life, they are fundamental to health. Without sufficient enzymes, all nutrients, including vitamins, minerals, and trace minerals, cannot be utilized properly. That's why an enzyme deficiency can be so devastating. Individuals who are enzyme deficient are prone to a myriad of health problems and accelerated aging. Studies indicate that those suffering from a number of chronic ailments, such as arthritis, diabetes, allergies, skin diseases, cancer, and immune deficiencies, have one thing in common. They all suffer from deficiencies in enzymes or low enzyme levels. Enzymes are found in raw foods. However, with today's environmental pollution, raw foods are tainted with residuals of chemicals and cancer-causing agents such as pesticides. In addition, enzymes are destroyed when being heated above 50 degrees Celsius. All forms of cooking, frying, microwaving, destroy nutrients to some degree, but they destroy 100% of the enzymes. So there are no enzymes in cooked food. The extraordinary benefits of enzymes: strengthen the body's immune system, alleviates tiredness and boosts energy levels, improve digestion and absorption of nutrients from food, minerals and vitamins, improve metabolic cell function, promotes healthy cholesterol level and blood pressure, enhance skin and complexion, general maintenance and wellness.
How about that about no cooked foods have enzymes? Did y'all know that? That's kind of scary. Let's see what this one has.
Cooking dinner change the enzyme. I change the shape. Once you change the shape, they can walk around.
Enzymes. Nature's microscopic organism. Hi, my name is Henry.
Gotta be quiet,
This
isn't
is a presentation of how enzymes work. An enzyme is a living protein inside our bodies that helps us speed up reactions. It does this by lowering the activation energy of the reaction. This is my life. Milo is an enzyme. This is Milo's activation site. This is where a substrate will bind on and cause a catalyzation. However, only a specific type of molecule will fit this site. Oh, here comes one now. This is Ernest. When he sits on Milo, he will split into two separate molecules. And as you can see now, we have Pete and Bertrand, who are pushed every enzyme. Milo, as you can plainly see, is an enzyme designed to break apart substrates. Remember, Milo didn't start this chemical reaction. It would happen regardless of whether he was here or not. He just speeds up the reaction. Now, let's say we have another enzyme. Larry the enzyme. Larry will attract two separate substrates. Here they are, Sylvester and Orlando. Like Milo, Larry seats the two substrates in his active site. However, unlike Milo, Larry fuses the two together and now pushes one single molecule in. Steve. This animation was brought to you by
Thank God for that.
What about with project?
Let's look at that last one. There are all kinds of animations. I've looked at maybe 30, 40 of them, so I decided I like these. I don't care much about Steve and all those characters, but it shows you how it works.
Here's an example of a chemical reaction. One large compound is broken into two smaller compounds. This reaction takes place much too slowly to be useful in a cell. In order to speed up chemical reactions, cells make special proteins called enzymes. An enzymatic reaction begins when a specific compound binds to an area on the enzyme called the active site. The compound that binds is called the enzyme's substrate. Notice the shape of the substrate and the active site. They fit each other like a lock and key. In general, each enzyme's active site can fit only one kind of substrate, and so can speed up only one kind of reaction. When a substrate binds to the active site, an enzyme-substrate complex is formed. A slight change in the shape of the substrate weakens a chemical bond. This weak bond is easily broken, splitting the substrate into two pieces. The pieces, now referred to as products, detach from the enzyme. In enzymatic reactions, only the substrate is changed. The enzyme itself is unaffected by the reaction. After the products leave the active site, the enzyme is free to speed up another reaction.
They would split anyway, but much faster with the enzyme they're waiting apart. We're done.